Welcome to this webinar about the newest developments in Beta's product suite in the domain of electromagnetics. I am going to present you the Azeris plugin, which is a plugin that allows the user to prepare and set up electromagnetic simulations in ANSA for the Azeris solver. Its development started in version 23, and it's the first version where it came out. And first I will perform a short introduction to boundary element methods in electromagnetics. Then I will talk a little bit about what Azeris actually is. I will describe the interface in terms of materials, domains, illumination, lamp elements, and validation and export tabs. And all this will be done during a live demo. So what is the boundary element method in electromagnetics? It is one of the most popular numerical methods for the exact, or as we call it, full wave simulation of electromagnetic fields. And it has risen significantly in popularity and use since the invention of fast iterative methods like the fast multiple method in the early 90s. The principle of this method is to set up integral equations on the boundaries of objects and to solve for the boundary values of electromagnetic fields. And there are significant advantages in boundary element methods. First of all, obviously you need to mesh only the boundaries of objects and not the interior of objects, so you have only a boundary mesh. So that means that you have less elements and reduced degrees of freedom on which you have to solve. And finally, you can calculate the exact electromagnetic field values anywhere you like without being bound to a mesh in the post-processing stage. The basic principle of boundary element methods is a very old principle called Huygens principle. This principle is represented best from the picture on the bottom of the slide, which tells us that the solution of a linear wave equation is fully defined by the boundary values of the field, for example, for an acoustic field is pressure or velocity, on a closed surface. And the intuitive explanation is that for a wave field, each point on a closed surface, on a closed wavefront, for example, acts as an elementary spherical wave source, a secondary point source of spherical waves. And the individual spherical wavefronts at a later time overlap to produce a secondary wavefront so that the wave can propagate. This principle tells us that if we know the boundary values of the wave field on a closed surface, we can calculate the field values anywhere else by integrating on boundary surfaces. In the case of electromagnetics, the unknowns that we have to calculate are the electric fields and the magnetic fields, or H fields as we call them, on the surfaces of the objects. The E fields give rise to magnetic currents, and the magnetic fields give rise to electric currents on boundaries. And the typical situation that arises in such problems is represented in figure 1 on the right, where you have multiple objects which can have contact to each other or not. And some of them are transparent, or as we call them in electromagnetics, dielectric, and some of them are metallic, or as we call them, conductive. The transparent are depicted by white and the conductive by gray. And this means that the electromagnetic fields can penetrate the white, the transparent objects, but they cannot penetrate the metallic objects, the gray ones. And what we need in electromagnetics in boundary element methods is to calculate actually the fields only on the surfaces of these objects and interfaces between the objects and not inside these domains. So that's why we discretize only the surfaces. And we need to know for each shell element, which boundaries it separates. Does it separate the interface between Di and Dj or Di and Dk? So this is very important. And the boundary conditions are either implicit or explicit. So the implicit boundary conditions are that on dielectric domains, the two unknowns, the electric and the magnetic currents, are equal on each side of the interface. And for conducting domains, the magnetic current is always zero. So you have only one unknown. And each dielectric domain, so each white volume on the right, as you see it, gives rise to its own pair of integral equations. And in the end, we combine all these equations to produce the final system of integral equations which has to be solved. So what is important to define for the user is to define the type of surface. We have, for example, these three types of boundaries. We have diel-diel, or dielectric-dielectric interface. We have dielectric PEC, which is short for perfect electric conducting. And we have lossy surfaces, which means that they are bounding metallic objects, but these objects are not perfect. They have finite losses. So this means that the electric and magnetic currents on these surfaces are related via constant material parameters.
In such problems, we have two categories of examples. We have scattering problems and radiation problems. The scattering problems are problems where the objects are passive. They are the receptors of impinging electromagnetic radiation. So in scattering problems, you have an external source which illuminates the object. It radiates radiation onto the object, and the object scatters the incoming radiation into all directions. So such examples are, for example, radar applications. As you can see on the picture on the top right, the basic principle of radar is that you have a transmitter antenna, it emits some radiation. The radiation impinges on a target like an airplane, and it gets scattered in all directions. And you want to know how much is scattered, for example, in the direction of the transmitter, in order to calculate the strength of the signal, to see how big the radar signature, as we call it, is on the radar. Another example of scattering problems is the microwave imaging applications. For example, you can have in the top left picture a circular array of antennas which irradiate a part of the body, and where the body has a tumor, and you want to detect the position and size of the tumor. So you emit radiations from the surrounding antennas, and the tumor scatters the radiation. The scattering radiation is received by all the antennas around it. And by suitable mathematical methods, you can reconstruct the position and the shape of the tumor. So in case of scattering problems, the excitations, the loading is analytical. It's not positioned on the mesh. It's an analytical equation which is internal to the solver. So you can have plane waves incoming from the infinity. You can have spherical waves from elementary dipoles somewhere in space, or you can have even a pre-calculated imported field of an antenna. On the other hand, radiation problems are problems where the object itself is active. It acts as a radiator. It emits radiation. And it's activated by local voltage sources on edges of the mesh. And the basic applications are, of course, antenna applications, where the object we want to study functions as an antenna. It emits radiation. So let's go next to the solver that we started supporting with ANSA, called AZERIS. AZERIS is a boundary element solver for electromagnetics, whose exclusive distributor is Emacs, also creator of the Sonate acoustic solver, which is also supported by Beta CAE. Emacs develops and maintains scientific computational software for major companies like Airbus, MBDA, Thales, and so forth. And it has a fairly standard workflow. So it consists of three groups of executables. The first stage is the pre-processing. So you execute the executable called ANADEL, which converts the mesh to the degrees of freedom that you need for the electromagnetic problem. And it also calculates some other quantities, which I will not go into right now. The main stage is the ELFI-POL solver, which performs the matrix assembly and the solution of the linear system. And finally, you have the post-processing. So the values that we get from the solver cannot be used directly for physical quantities. They have to be derived from these. In the post-processing stage, you can calculate physical quantities like charges, electrical currents, near fields, far fields, radiation diagrams, etc. So the workflow is you have as an input a pure mesh or a pure CAD geometry, but it has to be meshed before running the interface. And you can have also another database which can be meshed or just geometry. Then you set up the simulation with our plugin. I will talk about the different stages later. And finally, you output the files that you need for the simulation. So you export the mesh, and you run the preprocessor ANADEL from our GUI. Finally, you export the P01 file, which is a driver file for the solver, and the batch script, and you run the script and you perform the simulation. So the general workflow is as follows. You go from ANSA, you import your mesh, you set up the simulation, the boundary condition, the pre-processing, and the solver settings. You run the main solver called ELFI-POL, you run the post-processing modules, and you visualize the results in Meta. So let's go to the summary of the plugin. This plugin has been implemented as a plugin since ANSA version 23, so it's very new. It can be accessed from the same category as the ECAD importer. So it's in the group Electronics and Electromagnetics. It is a tabbed environment. So let me open the environment of this. Let me open a new file to show you the environment. Okay, I have a model here. I'll open my environment. So this is the interface. It is a tabbed environment which has various categories. Some of them are more or less independent of the other. And each tab has also some side tabs, which can be used for navigation inside the same tab. In general, the direction of preparing a simulation is from left to right. The final stage is the rightmost, and from top to bottom. For example, here, first you have to define domains, then interfaces, and then cables. But it's not very strict, so you can do some things before some other things. This is just a general direction for the user. So what does every tab do? Let's go first to the domains and boundary conditions. So before defining domains, it's good to have some electromagnetic materials defined. And there are three types of materials supported in Azeris. There are volume materials, surface materials, and line materials. And all three material lists are displayed in this tab. You can add a new material to create any type of material you want. And let's see how we can do this. So let's go to materials. You have volume materials. Let's say you want a new type of material, for example, a complex material. And here you can see that we have various fields in this list. MID is the material ID that exists in the ANSA database. You can rename the material. For example, let's say this is air. You can change its type here, and you can edit the various arguments of this material, the various fields. You don't have to know the exact meaning right now of what all the arguments are. They are all defined in the manual of Azeris. If a field is not supported by the specific material type, its field is inactive and is not filled by any value. So if I go here to PC, this specific material does not support any fields, so that's why it's empty here. If I go to conductive, here you can see that all these five are supported. You can edit them here and here. The same holds for surface materials, where there are many types of materials here, and for linear materials. The same principle. You can change their name, you can change their type and the fields, and all the inactive fields are not filled by anything. Finally, there is the option of loading ready produced material databases as ANSA databases, so that you don't have to create materials every time. So there are two options. Either you load them after launching the script by merging. So let's load the demo materials here. Okay, merge. And now we can reload materials to see which materials we have loaded here. Or we can preload the materials before launching the plugin by merging the material database. And then when we launch the plugin, we will see that all materials that exist in this database have been pre-filled. Okay. So there are two options of loading material databases. So let's go to the next tab. Let's go to the domain definitions, which is very important. So what we call in Azeris domains is actually ANSA volumes. We define all the closed volumes, and to recognize them, we click on Recognize Domains. For example, here, when we get a list of the volumes that exist in this model, the closed volumes, you have the ID of the volume, the name of the volume, which can be edited. The material of the volume can also be changed and must be changed in order to have a full description of the model. And the type of the volume is the type that I told you about in the beginning. It's either transparent, which is called dielectric, or it's non-transparent, which is called either PEC, perfect conducting, or IBC, which is imperfect conducting. The only exception to the rules I told you before is the EXT volume. Here, the volume with zero ID. It's not an ANSA volume, but it represents the exterior domain, the unbounded domain, which lies outside of your model. But it needs to be there because it needs to have material. So how can we see which volume is which in our model? We have the highlighter here. So here, this is our first volume. You can also isolate it by right click. This is the other volume, and this is the third volume. So let's rename them so that we can know which volume is which. This is a patch antenna. It's a standard antenna in electromagnetics. You have a printed patch. Let's turn to PID view. This is the patch on a substrate, and you have a ground plane here, and you feed it by a coaxial cable which excites the patch and radiates as an antenna. So let's say that the first volume here, as you can see, is the substrate. Let's say sub. The second volume is the coating of the coaxial cable. Say coat. And the third is the core cable of the coaxial cable. Okay, let's say core. Now we have to assign materials. So we double click on the material here. We get a pop-up list with all the available materials for volumes. So let's say we have air for the exterior domain. Let's say we have FR4, a standard material for printed circuit boards. For the substrate, for the coating, we choose Teflon. And for the core, we choose PEC, which means actually perfect electric conductor, like metal. So now we have finished the definitions of our volumes. And this stage has been completed, which is designated by the green check mark. So we can go to the next stage, is to recognize the interfaces between the volumes. So let me recognize the interfaces. So now what do we see here? We have a list with various fields. Each interface is represented by a PID, and the PID is listed here. You have the group name, which is the naming of the PID, and it follows a convention which is needed by the solver to understand what the interfaces separate. You have the type of the interface, which can be edited by the user. You have the material of the interface in case a material is needed. Not every interface needs a material. You have the name. You can rename your interfaces, the suffix here, 1, 2, 3. And you have the domains. So you know which domain this interface separates. And you can also highlight the different PIDs, the different surfaces. So you can see here which are these. So the plugin does an educated guess about the type of the interface, but sometimes it leaves the choice to the user, for example here, for the undefined interface. Before going to the definitions, let me describe to you what kind of interfaces there are. So we have the following types of interfaces between volumes. As I told you before, we have dielectric, which is the common interface between dielectric domains. We have dielectric PEC, which is the common interface between a dielectric and a thick, perfect metallic domain. We have dielectric IBC, which means impedance boundary conditions. This means that this is the common interface between a dielectric and the thick, lossy metallic domain. We can have a PEC interface, which means that in the interface between two dielectric volumes, there sits an infinitely thin metallic patch. We have model surface, which is not fully supported right now, but it's there. It's for applying an excitation at the waveguide port opening. And you can also ignore some surfaces. What can also be there is you can have free sheets of material, so free surfaces floating inside volumes. They are not interfaces. They are included entirely inside volumes. And they can have these 4 different types. So they can be perfectly conducting, they can be resistive, they can be conductive, and they can be also ignored. So let's apply all this to our model. We can see here, for example, that this is undefined, but we know that this is the patch of our antenna. It has to be metallic. So let's say that this is a PEC interface. Then we have this material here. This is the ground plane, which is also metallic. So we say, okay, this is also PEC interface. And the rest is this surface which separates the substrate from the air. So this has to be the electric. Now we have defined these materials, but we are not finished yet. We have to define correctly the cable. So let's go here. We can see that this is dielectric, but we need an outside coating for our cable. We cannot leave it unshielded. So we will define it as PEC interface. So the outer surface will be metallic. This surface for later on is not needed, so we'll ignore it. And this is actually correct, the definition. This is dielectric PEC. But now we have another problem. We don't want this opening to be metallic. So in order to do this, we can define a part of the surface as a different boundary condition. So we say go to define boundary surface manually. We go to the selection according to feature area. We select this. And now we have a different boundary here. And we say, okay, this is the opening of the waveguide. We want it to be a model surface. And now we have completed the definition for this model. So this is how you complete the boundaries, definitions, and the interfaces for this antenna. And we have finally the category of cables, but in order to show you the cables, I will open a new model. Let's input the only supported format for simulations is ideas format. Okay, so it's UNB. So this is another model where you have a ground plane. So this is just a plate with two cables running parallel to each other. So let's open the plugin again. Let's redo the same things. Let's also load some materials. Okay. Let's start to recognize the domains. So here there is no closed volume, there is only the external volume. Let's say that it's air. Let's recognize the interfaces. So right now, as you can see, we have only two interfaces, which are sheets, actually. They are not interfaces between volumes. We have this one. Okay, I can choose to ignore it, for example. And I want to simulate only this ground plate. Okay, so this type is PEC. I could also change its type to make it resistive, but then I would have to choose a resistive material. Okay, let's keep it PEC. And let's also add another definition. Let's say that I want a part of it to be perfect and a part of it imperfect. Okay, so let's use, for example, this part I want to be imperfect. Okay, let's say this is resistive, so I define it as resistive. So now that all materials have been defined, we have a full definition of interfaces. And we can go to the cables. So the cables are the connectivity groups of line elements. If I recognize the cables, I can see here, and I can also highlight them, that I have three cables here. I have one cable loop here, and I have two cables running parallel to each other. Okay, let's say I will ignore this cable, and for the other cables, I will choose this type of material. So we have finished with the cables that are present. After defining the materials of the cables, we have finished also the cable definitions, and all these three ticks means that we can move on to the next definitions. So the next tab I want to show you is the illumination tab, where we can define frequencies. So there are four categories of frequency definitions. You can define either a single frequency. You can define a linear distribution of frequencies from one, for example, let's say from 100 Hertz to 1 gigahertz with a step of 10 Hertz. This would give us an enormous amount of frequencies. You can have exponential distribution frequencies, for example, from 100 Hertz to 100 megahertz. And how many frequencies per decade? Let's say 3 frequencies per decade. Or you can have a file where all the frequencies are defined here. Don't pay attention to this field right now. It's not important for now. So let's say, for example, I want to simulate this at 1 kilohertz. Okay. And what else can I define in this tab? I can define the additional illumination sources of our model. These are the analytical sources I was telling you about for scattering problems. So here you have a list where you can arbitrarily add sources like a plane wave. Here you have the parameters of the plane wave. You can add point source, you can add a Hertzian dipole, you can add a dipole array, you can add a dipole list, and you can add a binary file with results. And of course you can have multiple types of the same. So you can have multiple instances of the same type, like 3 plane waves, where each of the plane waves has different parameters, for example. So you can see that you have 3 different plane waves. You can arbitrarily delete sources here. And you can edit all the attributes of each analytical illumination type. All this is documented in the manual of Azeris, so Azeris users know what they have to fill in here. For example, for the plane waves, you have the direction where the plane wave comes from, and you can have a whole array of directions. You have a window on a unit sphere, which is defined by spherical coordinates theta and phi. And you can say, my plane waves come from a direction from 0 to 90 degrees with 1 degree step, and I want just a single azimuth value. So this means that you will have 91 different plane waves coming into your model. So this is actually 91 different simulations that will run here, because you have 91 different excitations. So after showing you this tab, I will go to the next tab, the LAMP elements tab. So here we define junctions between wires and plates, and we define also local lumped sources, also local sources of excitations. So first of all, let's go over what junctions are. So junctions are the points of connection between cables and surfaces. And Azeris does not need topological connectivity between the line mesh and the surface mesh. As you can see here, there is no topological connectivity. The nodes of the surface mesh are independent of the nodes of the line mesh. The way Azeris understands that there is a connection between the surface and the wire is that it puts the end node of the cable and two edge nodes of the surface mesh in the same set. And the set has a specific convention, but you don't need to know all of this as a user, because all of this is done automatically by the plugin. For now, let's turn off this option. I will tell you later why. I'll say, okay, auto detect possible junctions. All junctions between the cables and the surfaces have been found. Let's highlight them to show you what I mean. For example, okay, this is a junction where we have the end of this cable is joined to the edge that is defined by these adjacent triangles. And there is the option of aligning the junction. So for numerical reasons, it's best if the endpoint is at the geometrical midpoint of the edge. So we can say align, and now the elements are moved so that it's in the middle. And we can do this alignment. We can also delete the junctions here, and we can auto-align all the junctions. So now you can see that all the junctions have been auto-aligned, so you don't have to do anything yourself here. And there is also another option here, the detection tolerance. This concerns the distance between the end of the cable and the surface. How large can it be until the junction has been found? So here it's 5%. This 5% means that if the distance between the surface and the end point of the cable is less than 5% of the length of the last element, then it's considered a junction. Otherwise, it's not. There is no junction found. Finally, let's go to voltages and impedances. So here you can define voltages on this cable. You can have 3 types of voltages, and the active types are even more. So you have 5 types of active voltages. We can have a passive voltage, which means this is actually like a measuring device, or you can measure the voltage, and you can have an open circuit. So let's say I want a complex voltage source somewhere here. I select one node of the grid and click middle click, and I get my voltage here. I can highlight it, and I can edit all the relevant fields of the voltage. So I can say, okay, I have an internal resistance of 10 ohms, and I have an amplitude of 12 volts and imaginary part 0, for example. So you can define this way voltages on cables. I will later show you how you can define also voltages on surfaces. You can also define the impedances, so passive elements like resistances, capacitors. Let's say I want a real impedance somewhere here. Now you can also do a 2-click definition by clicking this 2 nodes here. Okay, this is a complex impedance, and yeah. And you can, here it is, yes. And you can edit its values here. You can have a complex impedance of, let's say, 50 ohms and 1 Henry. And let's say 1 nanofarad, let's see. Okay, and finally, in order to show you how you can define voltages on surfaces, I will open another model. So this model is a cube which has a lid, a door. There is a gap between the door and the rest of the body of the cube. So there's a gap here. Let's open the plugin. And let's go to the sources. So here I can define also voltage sources across these gaps. So I can say, okay, across this gap, I have a concentrated voltage source. So for example, I can define a voltage source here. And how I can define it, I can either choose one node and middle click, and I have this definition. So the definition of a voltage source across a gap is the following. You put the 4 nodes in a set, they are put here, and one triangle in a different set which characterizes the direction of the polarity of the source. But you don't know to need all of this, it's done automatically. So let's say I define an impedance, a complex impedance here nearby. I can also choose 2 nodes in order to define which edge I want. Because if I select only one node, the closest node on this edge will be chosen. If I choose 2 nodes, I can select whether it will be the right or the left of this node. So here I have 2 sources, one voltage source and one passive impedance. And you can see that the corresponding sets have been automatically created. So this is the J2, G2 set are used by the solver to characterize the existence of a source here. Finally, let's go to the validate and export tab. This is the final stage. Here you first define all your paths. So for example, here you give the project name, let's say test, and there will be a folder called test created in this project location. So in the models folder, there will be another folder called test in the end, and all the solver files will have the base name test and the respective file endings. You have to define the installation path where all the executables are found of Azeris. You have to define the license path. You can have also network licenses and a temporary directory. Let's leave it like that. And after defining the paths, you go to the tab of exporting mesh. Here you have some pre-processing options. For example, the low frequency option is used whenever the wavelength of the radiation is much larger than the edge length of the mesh. But this is just for the user. He has to know whether he has to use the low frequency or not. There are also other options like overriding the default UNV units or not. And there is also an option for exporting all the executables for either operating system, for Windows or for Linux. The pre-selection is the current operating system. And if you press this button, the mesh will be exported and the degrees of freedom will be processed. So the Anadel preprocessor will run and it will create the degrees of freedom file. And after this, you're almost done to start the simulation. You just have to go to the final page where you set all the settings options of the solver. So you have 2 main groups. You have the resources of the solver, how much RAM it will use and how much memory. So here you can choose how many threads it will run on. Also for a specific solver, how much memory it will use and so forth. And then the solver options. Here you can choose what kind of solver you want to use. The low frequency solver does not work for FMM. So these are the 3 different solvers that are available. The direct solver is the slowest one, but it can be used for small problems. You have 2 fast solvers, the fast multiple method and the hierarchical matrix method, H matrix. You can choose the precision. You can choose what kind of low frequency options you want. If you choose FMM options, then this group is active for the accuracy of the FMM. All these options are documented in the manual of the Azeris, so the user has to know them and if he wants to use them. You can finally put a description here, which is going to be written in the file of the solver, and then you press export solver files and you get your batch files and your solver files. So in order to show you a full demonstration, let me open a new file to demonstrate the full workflow. So what we have here is a fully meshed UAV model. This UAV model has two peculiarities. First of all, there is a gap here. So this means that there is a hatch with a hatch door and a gap. So we want to see how much radiation is going to leak through the hatch if we irradiate this UAV with a radar from outside, or if somebody else irradiates our UAV. And inside the hatch, if I show you on top of you, if I close the shadow, inside this compartment, there is a cable. So we want to see how much current is induced in this cable. And this compartment is separated by the rest, by the back and the front of the UAV with two surfaces. And we also have a dipole antenna radiating closely to the top of the UAV. Let's say this is an antenna that is used by the UAV for communicating with other UAVs or other ground stations. So here we have combined a radiation and a scattering problem. We want to see how this antenna radiates in the presence of the UAV, which is a problem called installed antenna performance. And we want also to see how the UAV is affected by external radiation. So we have a scattering problem. So let's start the plugin. Let's first load some materials. The materials, so that we don't have to load them later. Okay, so let us recognize the domains. We have the EXT domain, which is air. We have the back of the plane. Let's say, okay, this is back. And let's say that this is filled with some kind of stabilizing material, like let's say Teflon. And we have the nose of the UAV, which is, let's say, also Teflon. Okay, so we have two closed volumes and the exterior volume. And then we recognize the interfaces. So what do we have here? Let's highlight them to see them one by one. Here is the nose. So the nose, let's say it's a metallic sheet which covers the Teflon material. So we say it's PC interface. So this one is actually the interface between the nose and the compartment in the middle. So it's dielectric. This is the nose, which is, as I told you, has a metallic covering. So it's PEC. This is the interface between the back and the middle compartment. So it's dielectric. And this is the back. Let's say that is also covered by metal, like say PEC interface. Okay. And now we have two sheets. Okay, we have this, the door. Let's say that it's okay, it's perfectly conducting. And we have the walls of the middle compartment. Let's say that they are also perfectly conducting. And finally, let's turn off the highlighter here. We have fully completed the definitions here. Let's recognize the cables. We have two cables here. Let's highlight them. Okay, this is the one cable, which is the empty compartment in the middle. Let's see what kind of line materials we have. Okay, let's say this is copper wire. And we have the second cable here, which is the antenna. Okay, let's say that this is also copper wire. So we have finished the domain and boundary condition definitions. And let's go to the illumination. So I have chosen this model to have a mesh length that corresponds to 300 megahertz. Quick note that usually in boundary element methods, you need the mesh length to be lambda over 10 or lambda over 5, around this range to be accurate enough. It's best to have lambda over 10, where lambda is the wavelength. And another note is that the only mesh that is supported is triangular. You cannot have quad elements here. So I have my frequency here, and let's have my source. Let's have a plane wave that comes from the bottom, from down, let's say, so it comes from 180 degrees. So we have a single direction, and let's have a single direction also in azimuth, 0, 0. Let's have both polarizations. So I have defined my plane wave. Let me turn off the highlighter here. Let's go to the lumped elements. So here I want to see if I have any junctions. I have some junctions because this cable here is connected to the walls of the middle compartment. I have two junctions. The mesh has been a little bit deformed because we want it to be in the middle of the edge of the end of the cable. And here we have the other edge here. Yes. Okay. So finally, we want to define some excitation for our antenna, else it will not radiate. So let's define a complex voltage source on my antenna in the middle. Okay. Let's see. Yes, this is it. Let's say it radiates at 1 volt. And finally, let's save our model. Okay, now let's say this is the name. Let's put the correct installation path and the license path. Let's export the mesh. So now you see a message that the degrees of freedom were successfully processed. So let's go to my folder. Now you can see that the UNV file has been exported. You have some auxiliary files that have been created by running Anadel, and here is the log of the running, where you have some statistics and how the processor ran. And the final stage is to put some resources. For example, let's say I have 4 cores here and 4 cores here. I will use the H-matrix method. I will use this solver, and I will leave these options as they are. Let's put a description and export the solver files. Okay. So now the solver files have been created. The solver files are called P01. So if I open it, you can see that all the data I put in my GUI are here. The names of the domains, the material parameters, the cables with their material parameters, the illumination, the frequency of the simulation, the plane wave, the local values, which means the voltage sources, and so forth. And apart from this, we have also the script, which is called run lfitwhole. It has all the settings that I used, all the paths, so it's ready for running. In order to demonstrate it, I don't want it to be fed to the log. I will just show how to run it from here. Open in CMD. So the solver is ready to run, and you can see all the messages of the solver. So this model will take maybe around 5 minutes to run. In order not to wait, I will show you some results of the simulation. So let's go to Meta. And let's open the VTU file. So I told you that the results are in the ParaView format. So this is the geometry. And let's go to the results. We have one state. This is the frequency. And we have scalar and vector results. Let's load only the scalar results. So here we have a list of all the excitations. Here you can see that these are the plane waves. This is the plane wave, and this is the G1 port, which means this is the antenna. So if I load one of these, this will be the fields that have been excited by the plane wave. The G1 fields will be the fields that have been excited by the antenna. For example, if I want to see the electric current that has been excited by the plane wave, I will go here. I can see how it looks like. So here you can see the electric currents that are induced by the plane wave. And as you can see, the highest values are underneath because the plane wave comes from underneath. And on the top, you don't have so many currents. They are just the residual currents that creep around the surface. And if you want, you can see also what currents are induced when the antenna is activated, like here. Okay, so here you have the antenna. So not much is going on because the highest fields are around the antenna. But you can change the limits, for example, to 0.02, and you can go to logarithmic range. nonlinear spacing to have a better view here of the fields that are induced when the antenna radiates. So this antenna radiates, but because it radiates, it also induces electric currents on the surface of the plane, as you can see here. Let's go back to this one. You can also have the charges, for example. Okay, let's say linear or recalculate auto range. So these are the charges that are induced on the plane because of the field, incoming field. Okay, let's go back to the antenna, recalculate. And now what is more, we can load the radiation pattern of this antenna. In order to do this, we either have to open a new model and load the radiation pattern, or we can load the geometry anew and load the pattern here. Load this model again in the same window. Okay. And if I go here, I have both geometries, and now in this geometry, I will load this file which contains the radiation pattern. Let's import the total electric field. So, as you can see, this is the total electric field in the far field. So what does this shape show us? It is actually a polar diagram in all directions of space. And it shows us how intense the radiation in each direction of space is. And it's indicated in two ways. In a deformation way, so the distance of the surface from the center of the coordinate system indicates the strength of the radiation. So as you can see here, most of the radiation goes to the top and some goes to the sides. And also, it's indicated by the color. So the red is more, green and blue is less. Let's put some range limits here. Here the colors are better. And you also have a way of changing the parameters of this radiation pattern. So this is a new tool that is present in Meta version 23. It's in results, far field. So here you have two sources, so that's why you can activate both, or you can deactivate one for the far field. So this is the main field of the antenna, G1. And you can, for example, scale it. You can say, okay, one scale 1. And furthermore, you can hide this PID here in order to visualize at the same time the currents. So let's go to the range limits again. Let's go to the 0.3 that were, I think it was 0.03. One active, yeah. Okay. And you can have both active, yes. And here is the antenna field. And this is the result of the antenna radiation. So you can have both active at the same time. This concludes the presentation of the new features of ANSA and Meta for the support of the Azeris solver. To sum up the general workflow, the user can set up his model including boundary conditions and solver settings via the Azeris plugin in ANSA. Then he proceeds to run the main solver and post-processing modules of Azeris. And finally, he can visualize a wide variety of results in Meta, including surface currents, near fields, and radiation patterns. Thank you for watching.